Hello everyone, I'm Liang Zheng from K Leuven. I'm glad to present our work, NeighborMAE, exploring spatial dependencies between neighboring Earth observation images in mask autoencoder pretraining. The main idea of this work is simple. In Earth observation, images are not isolated samples. They are observations of the continuous Earth surface. So instead of training mask autoencoder on each image independently, we ask whether neighboring images can provide useful spatial context for mask autoencoder pretraining. Mask image modeling has become a popular self-supervised learning strategy for Earth observation. The model masks parts of an image and learns to reconstruct the missing region. However, most existing MIM methods reconstruct a single image tile independently. This is a simplification of Earth observation data, because satellite and aerial images are naturally spatially connected. Neighboring images often share useful information, such as terrain structure, land use, continuity, roads, buildings, and infrastructure patterns. At the same time, neighboring views may also differ in acquisition time, viewpoints, or sensor conditions. This means neighboring images provide various signals, share spatial context, and natural variations. Therefore, we ask, can neighboring images provide useful context for mass image modeling? To answer this question, we propose NeighborMAE, which extends MAE from single image reconstruction to joint reconstruction of neighboring Earth observation images. The method has 5 main components. First, neighbor sampling. We use geospatial metadata to sample neighboring Earth observation images based on the intersection over union of their spatial footprint. Images with sufficient overlap are treated as neighbors. Second, relative position encoding. We embed the patch position in a shared normalized coordinate system, which allows the transformer to understand the spatial relationship between patches from different images. Third, joint reconstruction. Instead of encoding one image independently, we concatenate the visible patches from both neighboring images and fit them into the same MAE encoder. Then the decoder reconstructs the masked region of both images jointly. Through self-attention, the model can learn dependencies across neighboring views. Fourth, dynamic masking ratio. If two neighboring images overlap strongly, reconstruction becomes easier because one image may reveal information about the other. To keep the pretest task challenging, we increase the mask ratio when the IOU between the neighboring images is high. Finally, visibility-aware loss weighting. Some mask pixels in one image may already be visible in the neighboring images. This can create shortcuts when the model simply copies the visible content. To avoid this, we reduce the reconstruction loss weight for pixels that are visible from the neighbors when copying is too easy. Together, this design allows NeighborMAEs to learn from neighboring images effectively and efficiently. We compare NeighborMAE with original MAE under the same training conditions. The evaluation includes diverse downstream Earth observation tasks, including image classification and semantic segmentation. We evaluate both linear probing and fine-tuning. As shown on the right, NeighborMAE consistently improve over MAE across all downstream benchmarks. This result suggests that neighboring images provide useful contextual information, and that NeighborMAE learns more transferable representation than standard MAE. Next, we analyze where the improvements come from. A key question is whether NeighborMAE works simply because it sees more pixels, or because neighboring images provide more useful spatial context. To answer this, we compare different ways to extend the input view using the same extra token budget, approximately 2 times the base input used by standard MAE. The result shows that simply using a larger tile gives only limited improvement, In contrast, neighboring images provide stronger gains because they introduce richer spatial variations rather than a fixed, larger field of view. The best performance comes from multi-temporal neighbors, which combines the spatial variations from neighboring regions and temporal variations from different observations. This supports our main claim. The gain does not come merely from increasing input size. It comes from learning spatial and temporal dependencies between neighboring Earth observation images. In conclusions, this work highlights an overlooked signal in mass image modeling for Earth observation, the spatial dependencies between neighboring images. We propose NeighborMAE, a spatially aware MIM framework that jointly reconstructs neighboring EO images, which learns stronger and more transferable representation. Our experiment shows consistent improvement over MAE across diverse downstream tasks, and the ablation study confirms that neighboring views provide more useful context than simply enlarging the inputs. Thank you for your listening.